You know that calculator on your desk or on your phone? We use it all the time without even thinking about it. But have you ever really stopped and wondered what's going on under the hood?
I mean, how in the world does it spit out the answer to something kind of messy, like the square root of 9.1, in a fraction of a second? It's not like it has a giant phone book of every possible number stored inside. No, what it's doing is actually way, way cooler.
Here's the secret. It doesn't even bother finding the exact answer. Instead, it makes a lightning-fast, ridiculously accurate guess. And the amazing tool it uses for this little magic trick? It comes straight out of calculus.
So, today, we're going to pull back that curtain. We're going to dive into the exact mathematical secret that powers not just your calculator, but honestly, countless other gadgets and technologies you use every single day. The whole idea behind this is, well, beautiful in its simplicity. It's all about understanding that for a lot of really complicated problems, an answer that's close enough is, well, it's perfectly good enough. And this powerful concept has a name: linear approximation. So here's the big aha moment. Picture the graph of some wild curvy function. If you zoom in on any single point on that curve, and I mean really zoom in, like microscopically close, that crazy curve starts to look almost perfectly straight. It basically becomes the same as the simple straight line that just kisses it at that one spot. We call that its tangent line. And that brilliant little observation gives us this technique called linear approximation. What we do is we use that simple, straight tangent line at a point we already know to make a super educated guess about a point nearby that we don't know. It's a fantastic shortcut. And here it is. This is the secret sauce, the recipe that makes it all work. Now, I know what you're thinking. At first glance, it might look a little intense, with all the letters and prime symbols, but trust me, the idea behind it is incredibly straightforward. Let's just break this down into plain English. F of A, that's just our starting point, our home base, a nice, easy value we already know. Then we have F prime of A. That's the derivative, which is just a fancy term for the slope or the steepness of our curve right at our home base. It's like our compass. And X minus A, that's simply how far we need to walk away from home base. So you start somewhere easy, point yourself in the right direction, and take a small step. That's literally all this formula is saying. Okay, theory time is over. Let's actually use this recipe to solve our original mystery. We want the square root of 9.1. That's hard. But what's a number really close to 9.1 that's super easy to find the square root of? Yeah, it's 9. All right, let's plug in the numbers and see what happens. Our easy starting point, A, is 9. And the value there, f of A, is just the square root of 9, which is 3. Easy. Next up, we need the slope at that point. A little bit of calculus tells us that slope is 1/6. And finally, how far did we step away from our easy point? Just from 9 to 9.1, so a tiny step of 0.1. We plug all that into our formula, and we get an approximation of about 3.0167. And look at that. Our simple approximation, something we could almost do in our head, gave us 3.0167. And what does the calculator say? 3.0166. That is unbelievably close. That right there is the power of linear approximation in action. It's not magic, it's just really, really clever math. But wait, there's more. This whole amazing tangent line shortcut can be used in another really cool way. Instead of just estimating a final value, we can use it to estimate the change in a value. And for this, we have a related tool called differentials. Okay, think about it this way. On the left, you see the formula for the actual change in a value. Mathematicians call it delta y. And frankly, it looks like a bit of a headache to calculate, right? But now look at the right. That's the formula for the estimated change, dy. It's the change you'd get if you just walked along that simple, straight tangent line. So much cleaner, so much simpler. It's our calculus shortcut for figuring out change. So what this really gives us is a super quick and easy way to guess how much our output is going to change if we just give our input a tiny little nudge. We don't need the messy, complicated calculation. We can use the simple one. And this idea has huge consequences in the real world. Because, let's be honest, in the real world, our measurements are never perfect. There are always tiny little errors. And differentials are the absolute perfect tool for understanding how those small, innocent-looking errors can ripple through our calculations and sometimes grow into really big ones. Just think about this for a second. Let's say you're measuring a cube because you need to calculate its volume. If your measurement of just one of its sides is off by a teeny tiny amount, how much does that mess up your final number for the volume? Okay, so we take out our ruler, we line it up carefully, and it looks to be exactly 5 centimeters. Simple enough, right? But, our ruler isn't perfect. Our eyes aren't perfect. We figure there's a potential error of plus or minus zero point 0.1 centimeters. That's a tiny amount. It's barely the thickness of a credit card. You'd think it wouldn't matter much. Well, what happens when we calculate the volume? That tiny little error, the thickness of a credit card, doesn't create a tiny little error in the volume. Using differentials, we can estimate that it creates a potential error of plus or minus 7.5 cubic centimeters. Our tiny initial mistake got magnified in a big way. And to really get a handle on an error, we need a bit of context. The absolute error is just the raw number, our 7.5 cubic centimeters. But is that a lot? That's where relative error helps out. It compares the error to the actual size of the thing. And percentage error makes it even easier to understand. A 1% error is a huge deal if you're building a bridge, but it's nothing if you're measuring a coffee bean. Now let's take this to a planetary scale. Imagine you measure the Earth's radius, and your measurement has a 2% margin of error. That actually sounds pretty good for measuring a planet. But watch what happens. When you use that number to calculate the volume of the entire planet, that 2% error doesn't just stay a 2% error. It triples, ballooning into a 6% potential error. The significance of that initial mistake just got 3 times bigger. And that right there is really the big takeaway. The world around us is messy and infinitely complex. But these amazing tools from calculus like linear approximation and differentials let us cut through all that complexity, manage uncertainty, and find incredibly useful, good enough answers that, frankly, run our world. And this is not just some abstract math theory. This is the hidden engine of the modern world. Your phone's GPS is constantly using these kinds of approximations. The physics engine in a video game has to make thousands of good enough calculations every second to feel real. This art of approximation is what makes so much of our technology possible in the first place. So the next time you punch a number into your calculator, you'll know the secret. It's not magic. It's just a really, really clever guess. Which kind of leaves us with one last thought. Where else in our world are these powerful, good enough answers pushing us forward every single day?